So we're going to go through mass and energy today, which is the part of nuclear physics where we look at E equals mc squared, finally. Ultimately one of the most quoted physics equations, Einstein's famous equation, energy is equal to mass times the speed of light squared. The shocker of it, I guess, is that you can have mass and the mass can disappear and you can have energy instead, which is not something that we experience on a daily basis. But there it is. Now, we look at it in terms of the nuclear binding energy now, or the binding energy. The binding energy is difficult because you feel like you want it to be the energy that binds the nucleus together, kind of stored inside the nucleus, but it's not. It's the energy released when a nucleus is formed. So it's not the same as what you might think it would be. And the way we calculate the nuclear binding energy is we work out the mass difference when you go from neutrons and protons to the nucleus, which I'll show you an example of here for forming an alpha particle. Now, nuclear energy, binding energy, there's different units for it. So we use the atomic mass unit, U, to calculate all these values because it just gives us, I guess, nicer numbers to work with. 1 U is equal to 931.5 mega electron volts, which is also equal to 1.661 times 10 to the minus 27 kilograms. This data fact is on the front page of the data booklet, and this one here, that 1U is 931.5 mega electron volts. Now, this is how we would calculate the binding energy of an alpha nucleus. We take the energy, we take 2 protons here because that's what the alpha particle is made of, 2 protons and 2 neutrons, and then they form the alpha particle, right, or the helium nucleus. 4-2 helium nucleus. Now, if we look at the mass of these protons and neutrons, and again, this data, these numbers are given on the front of the data sheet, we've got 2 times this U plus 2 times this U. Now, if we add those together, we get 4.0319 atomic mass units. We can convert that into mega electrons if we want. Now, when we look at the mass of the helium nucleus, we can see there's a mass difference, right? There's a difference in mass between the protons and neutrons separately and the helium nucleus. The mass of the helium nucleus has decreased, it's lower, and that's because these, when they have come together, they have released energy, and the value of that mass difference is going to be 0.03037 atomic mass units. And then if we want to convert that into mega electron volts, we simply go into this bit here with this conversion here. And so we multiply it by 931.5 mega electron volts, and we go at about 28.28965 mega electron volts. So that's the binding energy of the helium nucleus. That energy is not in the helium nucleus though. That's the energy that would be required to rip these nucleons out of the helium nucleus and go back to having 2 protons and 2 neutrons as separate entities. So it's the energy required to split the nucleus. It's the same as chemistry. Bond breaking takes energy, bond making releases energy. So breaking this apart would take energy, forming it releases energy. So if that helps, but I just think the binding energy just is a bad, confusing name for it. Right. And obviously binding energy is how we work out whether we're going to have energy released in nuclear fusion and nuclear fission. Nuclear fission is the joining of 2 lighter nuclei, joining of lighter nuclei to make heavier nuclei, so this would be kind of a fusion reaction. Nuclear fission is when you take very large nuclei and you split them. This is an example of a nuclear fission reaction. We've got uranium-235 absorbing a slow-moving thermal neutron in thermal equilibrium with the moderator, but that's the next topic, splitting into 2 smaller nuclei and then also releasing 4 neutrons. So if we want to work out the energy released in this, we look at the mass difference, right? Now they would give you the mass of uranium. Often they give it to you in a little table. So they give you the mass of this, the mass of this, the mass of this in atomic mass units, and then you would look up the mass of the neutrons, which is on the front page of the data sheet. So if we do this first one, we end up with a mass difference. So we're going to add this together and then take it away from all of this. We're expecting this is going to be lighter because we know that some of the mass has been converted into energy, because that's the whole point of it. And we get a mass difference of 0.180 atomic mass units, which then, if I convert it into mega electron volts, gives us 168 mega electron volts. It's really strange to get so far into A-level physics, I think, and then just be like adding really long numbers together, like an accountant, but it is what it is. Now, this is another example of a question, so you could ask them to find the binding energy of this thing. So they give us the atomic mass, the mass of the nuclei, and then we just say, well, that's 27 protons and 32 neutrons, and so we just add the mass of the protons and the neutrons together, take it away from this mass here, and again, I know that if I'm going to rip this apart, I'm going to gain energy, so this is going to be the bigger quantity, and I end up with a mass difference of 0.5408 atomic mass units. So if I multiply that by 931.5 mega electron volts, I'll get it into mega electron volts, which is 503.8 mega electron volts. Now, I can then divide that number by the nucleon if I wanted to. I'll explain why in a second. Oh, not 59, not 59, not 95. So if I divide it by the number per nucleon, I get, in this case, 8.53898 mega electron volts per nucleon, right? That means the binding energy total for that nucleus is 503 mega electron volts, 504 mega electron volts, but actually the binding energy per individual nucleon. Now, this, looking at the binding energy per individual nucleon, allows us to compare elements and kind of figure out whether we're going to have energy released through fission and through fusion. And there's a little chart called the binding energy per nucleon, against graph of average binding energy per nucleon against nucleon number. So we have the nucleon number along the bottom here. So basically we start off with your lighter things, hydrogen, helium, lithium, we kind of slowly increase. Now what it looks like is this. It goes up initially. There are a couple of jumps. There's a jump, a couple of jumps and ups and downs, but it doesn't really matter. In general, it goes up like this, peaks, and then it starts to decrease like this. The binding energy per nucleon. Now, around here, you get the iron group. They are the most tightly bonded nucleus and therefore the most stable things. Most stable nuclei, most tightly bonded nuclei. This side here, right, this means these ones have less energy. And uranium-235, this thing here is one of the things that you'd find over here, right? And uranium-235, these have less binding energy per nucleon. Less binding per nucleon. And so therefore, actually, the nucleons, so the protons and the neutrons inside this, are kind of technically heavier, right? There's less of a mass difference in these ones here than there is in these ones here. So there's less binding energy per nucleon. It's easier to rip these nucleons out. So you can kind of think of it as heavier or more massive nucleons. Yeah, that's what I think of it as. It's not necessarily the best way. So now, if you have slightly heavier nucleons and then you move to a stage here, and this is the same position down here, all these ones down here as well, they also have less binding energy per heavy nucleons. So helium will be around here, hydrogen is down here, helium's kind of up here a bit. Now, compared with these ones here, these ones have the most binding energy, right? This is the most or more binding energy per nucleon. It's important to notice that this is per nucleon because actually uranium has more binding energy than iron, and it is any day of the week going to be that case because there are more nucleons in it. But the binding energy per nucleon, and this is to do with the parameters of the strong nuclear force, which is repulsive between 0 and 0.5 femtometers. From 0.5 to 1 femtometers, it is attractive, and then beyond 3 femtometers, it disappears to zero. But where it is at its peak, that's where you're going to have the most binding energy because the nuclei are most tightly held. So more binding energy per nucleon kind of means like your nucleons are going to be lighter within the element, right? So they're going to have less massive nucleons within it. So if you go from uranium-235 or from hydrogen, you've got less binding energy, so it's easier to rip them apart, and so your nucleons are going to have kind of like a less mass difference per nucleon. Then if we move from either hydrogen through nuclear fusion, and this section could undergo fusion towards something, you're going to release energy because your nucleons are going to effectively get less massive inside the nucleus, and that means there's going to be a mass difference that's going to be released. Same as this, if you go from these ones here, uranium-235, this is going to be fission. You're going to release energy if you go from these into, say, 2 of these. Now, it's tricky, but let me know if you want me to go into any more detail and explain anything again. The last bit is appreciation that knowledge of physics of nuclear energy allows society to use science and inform decision making. So I guess looking at these things, and quite often you can do a comparison of what's going to release more energy, fusion or fission, how much is it going to release compared to, say, a kilogram of coal, and then decide how society is going to plan to generate the energy needed for kind of the planet. A kilogram of uranium could produce enough energy for sort of like nearly 200 people for the whole year, which is not, when you think about what a kilogram of uranium would look like. A kilogram of fusion fuel, so deuterium or tritium, could produce enough energy for sort of 700 people for a year. So, but obviously fusion is more complicated. Again, if you want me to go over something again, just let me know.